Well, thank you and welcome everyone to this INCOSE Lunch and Learn session today. While everyone is joining, I'm just going to take a few moments to do a quick overview of INCOSE. First, we'd want to give a couple of shout outs. First to Mike Riley, our featured guest speaker, who we'll formally introduce in just a moment. And also thank you to the three previous speakers, Jeffrey, Timothy, and Philip. I saw Philip joined us today as well. You can find their talks on our GLNC YouTube channel. It's a public YouTube channel, and you will definitely be provided with the link for the entire series in our follow-up email. Also a shout out to the Three Rivers chapter and the Carnegie Mellon Software Engineering Institute for hosting this awesome series. And a special thanks to Jack Stein, who organizes these lunch and learns and pulls everything together with great connections and just wonderful sessions. So my name is Samantha Lutz. I'm from the Michigan chapter, and I'll be the host for today's talk with Michael. On behalf of INCOSE, I want to thank everyone for participating today. So a quick intro on INCOSE. Our mantra is a better world through a systems approach. To share a little more about INCOSE, we have 124 corporate members in our corporate advisory board, over 19,000 members. We also have 50 working groups. We have 65 chapters worldwide in over 76 countries. So I have my, I guess you guys can't see me, or maybe you kind of can see me in the window. I have my version of this Systems Engineering Vision book 2035 that was just published. It's available free. You can find it on the INCOSE website. And if you look at me in the window, you can see it's just got an amazing series of visual pictures about what INCOSE and our CAB members and what we see as the vision for systems engineering in the future. Completely free. We also want to share, we have 3 different levels of certification. We also have an academic council, and we would invite any members of different universities, if you're interested, to talk to us about joining our academic council. Our academic council, as it exists today, we're showing all our different representatives, and we're very active in our student divisions, and more are growing every day. So our chapters and group, like we mentioned, 76 countries divided into 3 sectors. So there's the Americas, there's the European, and the Asian Oceania. And that comprises our 65 chapters. And as is pointed out on the slide, emerging chapters are growing every day. This is a breakdown of our Great Lakes North Central region, which is what the acronym GLNC stands for. And this is showing a breakdown of all the different chapters in this particular region. Working groups and initiatives, connecting people together within the same working fields to, again, allow that synergy to happen within these groups. And then we can set some standards for systems engineering practices moving forward. And we have 55 different working groups. You know, a lot of us are into the MBSE. There's an MBSE initiative. There's defense systems, automotive, agile. So without further ado, Mike joins us today from the Carnegie Mellon CERT, and they are responsible for responding and preventing attacks on the internet. They were first launched in 1988. And Mike has a super diverse background. He has 12 patents, anywhere from signal analysis to high pressure fluid dynamics. He also has patents in the medical community as well. So Michael holds a master's degree in software systems engineering from George Mason University and a BS in electrical engineering from Gannon University. So Michael's work involves the development of a method to estimate the quality risk of embedded mission safety critical source code, CREW, or Code Risk Estimation Worksheet. So in this Lunch and Learn session, he's going to do an overview of this process and particularly discuss how they identify the risk associated with the modern software development channels. So I'd like to introduce to you Michael Riley. Thank you, Michael. I'm going to stop sharing.
Sam, thank you very much. I appreciate those very kind words. Let me start to share my screen here.
Okay.
Excellent. Hey, just a quick check here, Sam. Can you see the screen? Am I sharing?
I can,
yes.
Thank you.
So I'll go ahead and get started here.
Awesome, thank you.
As with all of our presentations, there's some legal copyright. But the purpose of today's discussion, we're going to walk through a methodology for assessing risk in source code. SEI focuses often on mission critical source code, but in general, assessing risk of source code allows us as systems engineers to have a general idea of where the challenges exist, specifically with development of either new source code or within existing source code. So we're going to focus on the quality risk. Where is risk associated in the actual quality of the developed source code? We have a methodology. We'll talk through that methodology here. There's some applications for utilizing our findings, and we're going to talk a little bit about where the future direction of this goes, how this type of a process can be utilized for ensuring that software developed in a much larger system is free or as free of risk as possible, so that the systems engineers can then move into different phases of life cycle as that product continues within its needs and with being able to provide that product with the knowledge that it can be maintained over the course of its life cycle. So let's get in here to risk. Anytime software is developed, there is a fair amount of risk associated with the development of that source code. Here I've listed things along the lines of schedule risk, budget risk, a variety of programmatic risks. All of these things come into play when you're creating new software. And so as a systems engineer, we see that the working hand in hand with software engineering often requires a little bit of oversight at times, a little bit of mitigation for where those risks might live at, and certainly a product planning if we're going to utilize, say, existing source code or source code that might have been legacy from other projects. So collectively, we know as systems engineers, we've got to get our hands around software, we've got to understand the risks associated with it, and we've got to be able to plan for how that software can be mitigated, those risks can be mitigated, so that we can have functional software with a low amount of risk going forward. So now let's take a quick look here at where do we see risky software? Where can it be found? Where does it exist within the code bases, and what does it cause? What are some of the major challenges that risky software brings to us? Well, one of the first things here is it's hard to test. It's hard to get your hands around all of the various paths within software. It might be prone to critical failures. At the worst times, the software could be sitting there and all of a sudden, maybe something breaks. Well, that's an indication of frankly, poor quality software. Life cycle, the maintainability. We know that software that's built today doesn't know about the threat of tomorrow or the need for changes of tomorrow. So we know up front that we have to be able to maintain software over a life cycle. One of the key phrases we might hear on a routine basis as systems engineers are, hey, I really don't want to go into that particular area of code. It's brittle, or it breaks every time I touch it, or something else breaks. That's an indication of poor quality software. So we also know that whether we're working with customers or whether it's our own internal products, we want to extend initial capability, especially on very successful projects, by adding new content. If we find that we have to refactor all the time, re-architect code for every small increment of change, once again, an indication of poor software quality. Cyber attacks. This is, at SEI, this is our bread and butter. We are looking to ensure that software is resilient to cyber intrusions, to the threat of the day, the threat of tomorrow. And how do we do that? Well, you can't do it with brittle code. If you're afraid to put in a mitigation or to put in a change, that's clear indication that you basically have some poor quality code you might need to take a look at. Reuse, whether it's legacy code being brought forward or whether it's developing source code that can be utilized in the future, all of that is part of reusing software. You want to be able to reuse high quality code that is maintainable and is somewhat resilient to the cyber attacks. All of that are other indicators why you want to have high quality code. And so that tagline here at the bottom, is there a way to characterize these types of risk for a given code base? Yes, there is. And that's what we're going to be talking about here in the next couple of slides. So when we first start talking about doing any sort of proposal or developing and putting something in paper from a quality aspect, well, let's take a look at what's already been done. There's a fair amount of work already in this space that any of us as systems engineers would have come upon at different times in our career as ways of guiding us in the development of, say, source code or the development of any system-based product. So let's first talk about the ISO standards that exist for software quality and product quality. These have existed for a while. These are nothing that SEI currently maintains. They're in the industry, in the open standards. And I would certainly encourage anyone on this call or any other systems engineer to know that they exist, to read through them and see how they guide any particular type of development. The Hersteller Initiative, very much a European automotive consortium type set of standards. It's out there. Once again, I'd recommend it. A variety of reads through it. When it comes to software safety, the DoD, Department of Defense here in the United States, has a variety of standards, and these are open source standards that folks can download content on and review. For example, 178C, the Software Considerations in Airborne Systems and Equipment, very specific in terms of software safety, but for a multidisciplined approach. US Air Force 91-119. This is probably the most restrictive, the most focused of any of the software safety standards that exist out there, and that's for nuclear weapon systems. Once again, in the public domain, it's very specific from a software safety point of view. When it comes to security, MITRE, SEI ourselves, we have published standards in this space for coding and software development in C, C++, Java. There's some work going on for other languages. But writing software that is secure requires a variety of knowledge, and learning what you learn in the classroom doesn't translate always to industry. So these standards help organizations and developers to truly build software that is resilient. Of course, the MITRE Common Weakness Enumeration, CWEs, these are published, they're out there. Folks that are developing software should have knowledge of these. They should be able to find CVEs, and of course, the cousin there is the Common Vulnerability Enumeration. When we start talking about operating systems and we start talking about all of the different tools that come into any sort of code base that might be from the third party, we use the term SOUP, or software of unknown provenance. All of that directly contributes to the quality and security of software. So these standards, the tagline here, these standards can also provide frameworks for characterizing the risks with any given code base. So that's what we're starting from. That's the work that's already been published. Let's dive just a little deeper here into these ISO standards. So what are they talking about? What do they really provide us with? Well, the 25010 product quality model talks about functional suitability. It talks about usability, maintainability. All of these ilities come into play when we're looking to identify the challenges that are associated, how broad are the challenges with software quality. And it's also within these standards that we start to break down the notion of structural versus functional quality. And that's an important characteristic that I want to drive home. Functional quality of that source code is the most common used way that we test for software today. This is about requirements. Does my software support the system level requirements? Does my software support the software requirements for any given product? Well, that's about functional quality. That is telling us that the software meets its current requirements. When it comes to structural quality, this is how well the software has been built. Can that software maintain things like reliability and usability, maintainability? All of those, is it testable? All of those things, they're not necessarily requirements-based. They're based on the structural development. If we have a very poor structural development, but yet it is able to functionally work, well, in many cases, many organizations would say, that's great, that's fine, we'll fix it later. And at that point, we have potentially some technical debt. But as we go forward, we're going to talk through how to set up an organization or set up an analysis package so that we go after the structural quality of software and not just functional. Okay, next slide here. So at a high level, what are the aspects of software quality? Well, we take a look here at the 6 aspects that are across the top of the page. Things along the lines in terms of software architecture. And I'll let you read through the rest here, but the notion is these 6 different aspects cover at a broad range the quality of that source code. In the case of the SEI, the Software Engineering Institute, we often focus on deeply embedded, real-time deterministic systems, things that you might find in mission-critical applications, things like medical devices that are potentially implanted might fall into that purview. Similarly, things that are in the transportation industry or the communication industry, they might fall within that critical systems arena. Other products that are that might not fall into those might have a user interface. So as you can see from our aspects, we haven't included anything about user interface code. We haven't really included anything about other areas of aspects that fall outside of the embedded systems window. So as we go forward through the rest of today's discussion, we're going to talk about these various areas, why they're important, and how we go ahead and provide some analysis behind them. So we talked a little bit earlier about structural versus functional quality. This right here, as I was saying again, is about the structural quality of that code. And when we assess risk across 6 different aspects, 31 different focus areas, our goal here is to provide a scoring mechanism across all 31 different focus areas that is common enough that we can abstract a total list of quality from across all of these different areas. Collectively, we'll take that and provide an overall risk score for the entire software base. We'll break it down in terms of the 6 aspects of code. But most importantly, other than your overall score, is which areas of code are weak, which areas of code can have additional mitigations placed upon them to provide a more robust system. That's our overall goal here. So when we look at software, we do so from the standpoint of challenged areas often. So in many aspects, as a systems engineer, when you're bringing in software from, say, a legacy system, you don't know how good that code is. You probably have results of a V&V process, but you don't necessarily have a general understanding of, is that software maintainable from a previous version of code? Is it secure? Can that particular software baseline be tested? Those are the types of things that systems engineers really need to understand as we understand the total risk to a program. In your particular organizations, you might want to look at things other than mission critical source code. We talked earlier about software that might have user interfaces. You can imagine software that is directing the activities of large data systems. That type of code would require a different set of standards that would also potentially have different focus areas or different aspects. So I would encourage you to potentially start with the slides that I give you today, and then add or subtract based upon your organization's needs. That's traceable to those standards that we talked about earlier, and whatever standards are in your industry, whether it's locomotive, medical devices, communications, etc. We focus on the C language, usually for RTOSs. But once again, if you're developing source code for other environments, like a user interface or like something that requires a variety of data management, you might use different languages. You might use Python for a lot of your data management. If you have a user interface, you might be using C# or Java. So keep that in mind as you might be developing what a code quality analysis package looks like for your organization. This is very important. We look at code only, with or without requirements design. All that's great, but at the end of the day, the quality of the source code has to be measured outside of the notion of, does this pass all my functional or my system level or my software level requirements? And the reason that that's important is you want to be able to take a look at things that are not known today, where software must be maintained. We don't know where all the security problems are going to be at in the future. We might have to put that mitigation inside of source code. We don't know what types of functions will be available or required of a particular product in the future. That has to be put into source code. Similarly, when it comes to maintainability. So collectively, we're suggesting that a code quality analysis process doesn't look at existing requirements as its baseline or design documentation. Those are nice to have, it's good, it helps, but the reality is we should be able to do this quality analysis without having that level of documentation. Once again, similar to documentation, it'd be great to have a subject matter expert, specifically when building the software or acquiring the software. But once we have it in-house, or once a software is available, we really don't need to have SMEs providing the knowledge of how the software functions, because it's important to take a look at it independently. We're going to talk later here in a few minutes about the tools, the metrics that are utilized when identifying quality of source code. And there's nothing that I can say about eyes on code that to diminish its input. Tools all day long help us to find areas within the source code or within the environments that we can go put eyes on. But for anyone who's ever used a static analysis tool, I can tell you out of the bat, there is absolutely going to be false positives. When we put eyes on code, if we're familiar enough with the language, we should be able to tell whether or not that indication that comes out of a static analysis tool is actually a false positive or if it's true. And so we can never take away from the human aspect of analyzing source code. So once again, just considering the source code, let's estimate its degree of risk. So we utilize an interval of 1 to 5 when we look at these different focus areas. We collect everything in a Microsoft Excel spreadsheet, and I'll provide an overview of that here in just in a couple minutes. But our risks are assigned from 1 to 5. The lowest risk is 1. And so just like the game of golf, you want to have the lowest score possible. The highest risk, 5, would be an indicator of some serious challenges. For example, if you duplicated significant amounts of source code, or even any amount of source code within a code base, and you have multiple locations doing the exact same thing, that's pretty high risk. If, for example, you have a variety of secure coding violations, if your source code, for whatever reason, exposes APIs that could fundamentally change or alter what the mission is, that's pretty significant. That's going to be a high risk area. So in general, we're looking to have the lowest risk possible. In the particular area that we focus in, which is the embedded real-time systems area, we've come up with about 500 questions that are spread across those 31 different focus areas, 6 aspects of code. Like I said, if your software package or software baseline utilizes user interfaces or large data management, maybe even routine updates to encryption, whatever your software baseline has, the questions that you bring into the quality side of it are going to be unique to your particular needs or your particular organization. But what we found is a lot of the tooling that exists that provides analysis help with source code, tools like Cycles Understand, or there's a tool out there called Lattice, or any of the static analysis tools, or code counter tools. All of that collectively brings in information that can be brought into such an environment so we can just assess how large any sort of problem is and compare it with the baseline of the rest of the source code. So things along the lines of metrics, values from static analysis tools, estimates from analysts, and then qualitative inputs from that we might see from maybe a drop-down list. These are the types of ways information comes into an analysis tool like the CREW process. Those particular inputs many times are, ideally we'd like to have them all automated, but in many cases we have to have that eyes on code that really gets in there to understand whether or not a finding from a static analysis tool is actually a true event or a false positive. The tagline here, hey, tell me about the level of risk in my code. Oh, okay. Well, let me ask you about 500 questions and then I'll tell you. So these aren't overnight taskers. These are maybe a month or so taskers, depending on the size of the code base. And we'll get in there and ask those questions internally, and then we'll tell you the actual risk level of your source code. And of course, there's a normalization process here. The normalization process allows us to truly gather and throttle the responses. It also allows us to normalize over across multiple developers, multiple analysts that are looking at that source code, so that we don't have any sort of runaway estimates. And then here, this particular line I really want to touch on, because as I stated earlier, when we look at the focus areas, we provide scoring for the focus areas and scoring for the aspects of source code. Those scoring values are where the real benefit here is. Not necessarily the overall score, but those specific areas tell us where to go and potentially make any changes, fixes, mitigations, rather than fix everything. As systems engineers, we're often responsible for these types of projects. And geez, I only have a limited amount of resources. Where do I got to focus them at? Well, oh, by the way, I'll tell you where you need to focus them at. Okay, so what goes into a CREW analysis project? Well, we're going to take all the source code. We really need to get after all of that. We need to be able to build that source code. And the reason I say build or construct that source code is because tools like PC-Lint, even some tools that are coming out of like Coverity, these are all static analysis tools. They're actually a part of the build process. And when you're compiling code, compilers might give warnings, might give flags. All of that goes into the static analysis of a source code base. We'll take and capture all that information so that we understand how many warnings exist during the actual compilation process. Having logs for that process is great. Knowing what we call a software bill of materials, SBOM. What are the RTOSs that are being utilized? What are the associated libraries that are with those RTOSs, if at all? What about the board support package that might come in there? Collectively, those are all part of the build environment, all part of the build needs. We want to bring that in. Unit test code, mockups, and supporting unit tests. Sometimes we'll find unit tests that's absolutely embedded in the code with compilation flags around it. Other times we'll find associated files next to or in the same directories as the source code. Unit tests come in a variety of methods. JTest, a Java-based tool is out there. However an organization provides that unit testing, that comes into play here. And it comes into play because we'll look at a particular metric called cyclomatic complexity. How many paths are there through a particular code base? And when we talk about path analysis, if we have 2 paths through a particular area of source code, well, I would expect to be able to exercise those 2 paths in unit testing. One of the big challenges that we've often found is areas that have very high cyclomatic complexities, areas above, say, 10 or 15, that don't have the supporting unit tests to exercise all those various path coverages. And so the higher the amount of complexity, the higher the amount of unit tests that are required for it. There's nothing completely wrong with having highly complex code, but if you can't test for it, then it becomes a problem. When we talk about versions of source code and versions of the compilers, all of that may be unique to a particular build environment. From our aspect, we would love to have it so that we can replicate and a compilation process as near as possible to what is actually being done by a particular organization. And I would recommend you do the same. If the counterparts in your organization utilized a particular version of a compiler, you want to get your hands on that same compiler. As compilers evolve, make sure that the changes that are associated for that new compiler needs are actually brought forward as well. So things that we have found is VMs, virtual machines, that contain the compilers, that contain the raw source code, the directory structure. Of course, there is licensing concerns for real-time operating systems like VxWorks or Integrity. Those particular type of problems that exist within an organization, hey, if you're allowed to have that license, take the VM, utilize the VM so that you don't have to spend a significant amount of time recompiling source code with your software engineers. You can actually just bring it across. That will save significant amounts of your time. Documentation that's nice to have when we're doing these analysis processes, things like ConOps in your development plan, your system requirements plan, your system design plan. All of those documents are great to have. They show a roadmap, they show intent, but as I've said earlier, when we're doing an analysis type activity, our mission set is truly to complete it without having those documents. That gets at the true quality of the structural side of source code, not just the functional side. Okay, so what goes into one of these processes? Well, we talked about some of the things that are good to haves and nice to haves. What are like the foundations and what is our process flow? Well, we start with the source code and we build that. We build that source code. And then we look at the unit test code, the build logs and any sort of VMs that's available. Those things are fundamental. If there's unique information about that source code that, hey, this is particular to an environmental concern, okay, then we need to know that too. If it only is intended to run on a particular processor and there is no very unique BSP, well, we need to know that too. The tools that we use, well, obviously the compiler for that particular source code, the static analysis tools, When you have a bunch of static analysis tools, and I would certainly recommend that any design and development team utilizes more than one tool. Collectively, the output of those tools, which usually involves the line, the file, the line number, you have to aggregate all of that. In doing so, if without it, you'll be duplicating work. Often, if you have a null pointer, it'll be found by almost every static analysis tool that you have out there. So certainly you wouldn't want to go back and take a look at each one of those. You want to aggregate all those outputs into one tool. Now there's a tool that's available that our counterparts inside of SEI, the CERT division, they've actually created a tool called Scale, capital S, capital C, capital A, capital L, capital lowercase e, Scale. And that is an off-the-shelf freeware that aggregates the output of a variety of static analysis tools. There's commercial tools. Like I said, I can't recommend them to anybody, but they're out there. Code X produces one of them. There's others. Those aggregate the outputs of all those static analysis tools so that your findings, and when you go back and adjudicate what your findings are, you have an idea of what those tools. You only don't have to do it once. Another thing that we take a look at is analytics. We've developed analytics. Organizations develop analytics, but collectively, when you're taking a look at a lot of output, you have to aggregate it and look at the high priority areas first. That's where your analytics come in. Human analysis is also part of our process flow. So we take a look at the tool output. We take a look at where eyes on code actually provide value. What can we pull from some of our tools like Cycles Understand or Lattice, bring into a process like CREW? Well, we're going to pull those directly off of the tools and put them into our CREW analysis spreadsheet. And the output is going to bring things like the scoring, the results, and then we're going to tell you very specifically what areas of source code are your challenge areas. Okay, so this is a list of some of the tools that an organization might use. These are some of the ones we use. I can't recommend any of these. Our rule isn't to endorse or to be very specific. These are some of the ones we use. There's many others, but this gives you an idea of what the types of tools are that you'll utilize in your environment. Hey, Sam, I'm going to take a quick process check. Is there any questions right here up until this point?
No, we don't have any questions on the chat yet.
Okay. All right. I'll keep going.
Okay.
So when it comes to objectives, what are the objectives when we're estimating code risks? Well, we have a variety of code level questions that really direct analysts. So we talked about these 500 plus questions. In our case, it might be more, it might be less in your case. But if we establish them before we start, we'll have the ability to manage a team of analysts that are actually looking at source code. And so I would recommend that you start with the levels of questions that are most important to your organization for potentially those 6 different focus areas like security and areas like maintainability, testability, et cetera. As many of those questions that you can answer via static analysis, put those to play. Things along the lines of, what's the size of the code base? What's the cyclomatic complexity of that code base? What's the level of unit testing in that code base? Path coverage. There's another one out there that's very common from Professor Koopman, a gentleman on campus. He has a particular process that he calls the Koopman spaghetti factor, where he takes a look at multiple different metrics associated with a particular code base to give you an idea of just how much of it is what he uses the term spaghetti code. All of that comes into play here when we're building a list of what questions to ask. Ideally, the static analysis tools, maybe even some dynamic tools, are agnostic. Our process is agnostic to any sort of tool that exists out there. So we don't want to combine, or we don't want to focus any of the folks we're working with or any of the analysis activities that we do to just 1 or 2 or 3 or 4 known tools. We use it for critical embedded systems, but as I've spoken about earlier, there is an entirely different set of questions that you might need for data analysis, large data analysis, or user interface type environments. We want to be code-centric in terms of very objective types of questions. Humans can be subjective in various areas. Ideally, every question would be completely objective, but in reality, we know that once we put human eyes on code, there's going to be some level of subjectivity. So the more detailed the question can be, so that the analyst is answering a specific question, leads to the direction of being more objective, although it's never perfect as long as you have a human in the loop. It's estimated, right? We don't know for sure. We can't say that this is a very specific to the second unit place or a second significant digit of this is your exact risk level. We can't do that. We estimate over the course of 1 to 5, 5 being the highest, and we talked a little bit about that. So our mission set here is to just identify those high risk areas of code for further mitigations. Scored deriving results, and the scoring remains consistent over numerous projects. Once you complete your initial set of questions, driving on projects over and over and over again starts to bring out in your organizations what level of code quality exists on one project versus another, versus its second iteration, its third iteration, et cetera. And so now you have a common baseline from which you're constantly measuring risk. That helps organizations to recognize whether or not they're getting better, where their challenges areas are. But the best portion of that question is, when I have to adopt legacy code, where does it fit on the risk scale? Is it truly better to adopt that legacy code or start from scratch? That's the big win here. Okay, so I'm going to share the next 3 slides are what you might find in an actual Excel spreadsheet. And I'm going to see if I can't share just temporarily what one of these things looks like from a Excel point of view. Yeah, I can do that. Okay. So we utilize this CREW process by using a spreadsheet that has a variety of tabs on the bottom. Things along the lines of standards, maintainability, fault tolerance, security, testability, et cetera. And so what I'm going to show you here on the left-hand side of the screen is I'm going to start walking through the areas of risk. Now, this is a notional project that we might have worked on in 2020, but it gives you an idea of what the aspects of code are. Those are those 6 different areas, and that focus area for where that source code lives at. So over here in architecture, well, that's an aspect, and there are 3 different focus areas: modularity, dependencies, and patterns. What are the design patterns? Are there any design patterns followed? What about dependencies of architectures? Do you have any cyclic dependencies where one particular area of source code is dependent on a second, and that second is dependent on maybe a third, and that third is dependent on the first area? Is there a cyclic dependency here such that if you make any changes, parts of that entire dependency graph might change? It's good to know. Down here, when it comes to standards, are there standards used in the software development process? Stylistic standards and criticality standards. Is it documented? Can we find it? Is there a coding standard that an organization used? All of that comes into a quality number from within our process. Is there a quality number associated with those standards? And that's what we'll put down here. Maintainability. Maintainability is certainly an aspect, but there's essentially 3 different areas within maintainability. The comments. If I'm maintaining source code and I'm going to be doing it over the course of the life cycle, well, the same people are not going to be coming in there all the time to make those changes. So what is the code comment ratio? Forget about the boilerplate up top for any sort of source code file. What are the comments that are associated with an actual method or function that's doing some real work. What's the clarity of that source code? Are there high-level constants? Is the code readable? Conditional compilations, those are important type areas. Reusability. Can source code be reused? Once again, another area of maintainability. When it comes to fault tolerance, is there things like value checking, error handling, error logging? Is it instrumented? Diagnostics, we look to receive diagnostics all the time. Is that available inside of the source code base? If it's not, and we don't know what's really going on inside that source code as it's operational, that might be a concern. And is there health monitoring? Health monitoring in terms of state of health, SOH, or diagnostic messages collectively, are they available? Do they come out of the system? When it comes to security, well, there's a variety of ways of looking at security. Is the source code defensible? Does it have, is it utilizing libraries that are outside of the source code that's been developed for the program? Those libraries may or may not have vulnerabilities associated with them. Are they using libraries? And if so, how are they mitigating against existing problems with those known libraries? The CVE database, the MITRE CVE database that's available on the internet to anyone, tells us what types of libraries, what types of operating systems, what types of applications have vulnerabilities. We'd look for that, and we'd look to see that if there are vulnerabilities, that they're mitigated. When it comes down here to testability, is the source code testable? Is there regression testing available if I do make a change to a method or function? Can I come back and test it? And then finally here, when it comes to complexity, we talked earlier about some cyclomatic complexities. If I do have a high cyclomatic complexity, do I have the unit test to support it? In general, for those practitioners that are out there, cyclomatic complexity, modified cyclomatic complexity of say 10 to 15 is pretty high. If you have greater than 20, some might say it's not testable code. If you have something as high as 20, then you better have significant amounts of unit testing to really truly exercise it. If we don't find that, if those things don't exist, well, then that's an area of high risk. So that's the worksheet in general, and I'll stop this, and I'll bring up back the actual slide deck that we were talking through. And let's see, so I'll walk through this one, here, well, you know what, we're coming up on almost 1 o'clock. Sam, is this a good point to take a break and any questions that might have come in, or take a pause? I'll take a pause here.
Well, there is a question, but
Okay.
I would invite you, Mike, just because of the nature of what you're speaking to, if you have more to elaborate on, we can certainly take some time into the question area. But why don't we deal with Bashir's question first?
Okay.
If I can read it, or if Bashir, you'd like to read it, just please unmute yourself.
Yeah, I apologize for my funny diction there. So in both cases, the process that you're talking about and looking at the static code analysis, because it's a static code analysis, nothing gets executed. So obviously no functionality involved. So that was the reason, the drive, the goal of the static analysis tool was to cut out the functionality.
Yep.
So it doesn't execute, so we don't have anything to do with functionality. So I'm trying to understand, what your process provides over and above what the static analysis tools do, because the common thing is still there, just the code, not the functionality, the structure of the code. So they hit those, and covariety, and we can talk about the relative merits about another time. But from a process viewpoint, what you're presenting is it should provide something over and above that. That's what I'm trying to understand.
Sure. I'm gonna walk up through to some earlier slides here, Bashir, and here we go. So when we take a look at the static analysis output, there is a variety of things that those specific static analysis tools go after. And it's usually the language itself and challenges within the language that it finds. But it may not tell us about a variety of other things. For example, I'll just start with value checking. Is there value checking that's coming out of a lot of static analysis tools? In many cases, there's not. How well instrumented is that code? Well, that's not going to be anything you'd find in a static analysis tool. When it comes to the architecture, when it comes to dependencies or the modularity of an architecture, you're not going to find that coming out of a static analysis. Similarly for patterns, you're not going to find that either. When it comes to the testing, you will find in many cases the complexity comes out of some static analysis tools, but it's not going to tell you about how many unit tests exists and whether or not you have the ability to do any level of regression testing.
No, but they do provide some of the, for example, the cyclic dependency. And
you'll find that out of Lattice. You'll find it out of Lattice, and you'll find it out of at least one other open source tool from a cyclic dependency standpoint, but from a modularity standpoint of how that might be brought across through multiple pieces of code, maybe not so much. So you're going to have to go in there and identify that yourself.
Right. That's a good point. The way I'm looking at it is, for example, when you see the diagram of the flow, especially a control flow, and you look at it, your 5 modules, and there is a horrendous amount of going back and forth, jumping back and forth. And then you say, hey, okay, so why are you jumping back and forth between these 3 modules? Move the tasks from one module over to the other one, so all that thing gets done over there, and you don't have this horrendous amount of jumping back and forth, which is a bad situation with the complexity. So on the one hand, you can say, yeah, it doesn't automatically tell you, hey, this is crazy. You're bouncing back and forth, wasting time, causing errors every time you do the transfer. On the other hand, you can say, well, you got the data that's being provided to look at it, and so we don't have to tell you that it's horrendous. So that's how I was looking at it. They do provide the data. You can look at your architecture and say, "Ooh, look at this! This is a mess. It's a jungle. It's spaghetti code," as you were mentioning, using that term. So that's why maybe I was not so clear about it. What your process provides, you're saying it doesn't provide that, but it gives you the data. You can look at it. So I'm just being selfish. I'm trying to find out those special nuggets that your process provides, and say, okay, that is not there in static tools. And
so for those that aren't familiar with the output of a large amount of static analysis tools, what you're saying is, or what your comments are about, hey, there's very specific information that comes out of these very specific tools. I'm looking at it from a much broader perspective across 6 different aspects, not just the outputs of some static analysis tools or some level of cyclic dependencies. I also want to understand across the board security, maintainability, reusability. So all of that is coming into play here. For example, code duplication. I'll find that if I can name about 2 tools that'll provide that to me, but I might not have that out of any particular set of tools within a particular organization. Similarly, when it comes to error logging, error handling, the whole notion of fault tolerances, those aren't specific to any sort of given static analysis tool. I need to go in there and look at it based upon my experiences of, if I don't have those, then we got some significant challenges. I do have a colleague here from SEI who by the name of Jay Marchetti, who works in many aspects of this particular process. Jay, it looks like you're looking to say something here.
Yeah, I would just comment that by way of analogy, you could look at it as though you go to your doctor and you want an overall assessment of your health. Okay, that's what we're looking for in code, and he might order a number of different tests, blood tests, MRIs, EKGs, a variety of tests. None of those tests specifically tells your health picture, so to speak. So the doctor then has the job of coordinating all the input from those tests, which might be akin to static analysis tools, and then consolidating all that information in an overall assessment of your health. And that's basically what CREW does with a variety of static analysis tools. Over, Mike.
Thank you, Jay. Bashir, I hope that gives you a general idea as to why
that was a very good analogy. I do understand those static analysis tools map very well to the test that the doctor orders. But the doctor has to put together again with the knowledge that he has and experience to coordinate and say, okay, you have a problem, man. So, okay, I get it. But, one of the other things, I really don't want to hog this time, but if you can elaborate on something that I know that at least my experience has been that the static analysis tools do not provide the stylistic criticality. Styles are oftentimes when we are looking at the code and say, okay, well, you want to do it this way, well, that's fine, that's your style. But the problem occurs that, that Sam's style is different from mine, from Jay's and Michael's. And when you see this amalgamation of different styles, I didn't think that was an issue, but you are saying that is an issue. So if you could elaborate on that.
Absolutely. A great question. And there's some uniquenesses here. So I'm gonna talk about development for a smaller processor, maybe a microcontroller that one individual works on, and then a processor that has maybe 6 or 7 or 8 people working on a development team. And what you'll find here is the stylistic standards, the stylistic methodologies that one person uses, they're going to be completely different amongst a team. So if an individual later on from a development life cycle has to go back in and make any sort of changes, that person who's going to make those changes, if they know the source code, there's not a problem. But if they don't and they have to go and find it themselves, that's where we have problems, or we have say some challenges. So there's standards out there like the MISR standard that exist. From a stylistic standpoint, there's multiple ones, and many organizations adopt one. It allows a team of developers the same set of guidelines as they're developing source code, as they follow that same particular standard, that can then be added as more team members come on board or modified for any particular set of challenges that come down. If you don't have those stylistic standards, then, as you pointed out earlier, yours, Jay's, Sam's, all of our techniques as we develop source code could be completely different. And that's very hard to maintain going forward, especially after changes are going to be required to a larger code base. Now, I do want to point out, when it comes to microcontrollers or source code that under 1,000 lines of code, that sort of thing, those stylistic standards don't really matter as much as they do to much larger processors. When it comes to criticality standards, these are things like secure coding rules. These are how the actual source code is implemented when it comes to weaknesses within the software itself. And so we want to reduce any sort of vulnerabilities that we bring into that particular into the actual development of the code. I'll just throw out null pointers, for example. Obviously, we wouldn't want to pass any null pointers for a variety of reasons. So that comes directly into that criticality standard that organizations often have to adopt as they're developing that source code going forward. So stylistic and criticality standards. That's one of the comments overview that I'd provide. Questions?
So, Bashir, are you set now?
Yeah, thank you very much. Really appreciate your
that was great clarification, Michael. Thank you. And thank you for the question, Bashir. That was very, very interesting. We do have a question from Jeff, Michael. His question is, the CREW methodology appears to be instantiated on the tail end of the project. Is that a reasonable perception? And Jeff, feel free to unmute yourself if you'd like to engage further in conversation. Thank you.
I'm going to go to one of the earlier slides here. For this is truly where we see CREW having a most amount of benefit. Yes, for an existing code base, it makes a lot of sense to come back and later apply CREW to an existing base. But as systems engineers, I think there's very few of us that have started with absolutely 0 lines of code on a project. Many projects start with the bringing over of some legacy code, at least from a prototype standpoint, to get started with. That's one of the more ideal ways to utilize the CREW process. So if I'm building, let's say locomotive 1, and then 10 years later I'm building a locomotive 2, that software that might have been on locomotive 1, I want to start with that, at least to the prototyping stage, and at least to get some wheels moving to do something. So before I go ahead and completely adopt it for locomotive number 2, I'm going to want to put eyes on it to really understand if it's maintainable. Does it come to me with a whole lot of brutal code? And if it does, well, I might want to either completely start over, or I might want to just address those brutal areas. So that's where CREW can be very beneficial for organizations. The other side of this is, if you have an organization where there's a lot of politics, and let's be fair, that exists in all organizations. If we want to take a look independently at that code to truly understand whether or not it has those pitfalls or such a significant amount of risk, and I have to make a decision of whether or not I want to either adopt something new, or to utilize legacy, or to utilize something from maybe a vendor might have provided to me, I want to be able to look at that and utilize a process that doesn't necessarily require the organization that I'm acquiring it from to do all this work. I want to do it independently of them. That's another area where CREW brings in a lot of benefit.
And so hopefully I'm unmuted.
Yeah, I can hear you fine, Jeff.
The purpose of my question, I've been involved in programs, software intensive real-time systems, where the program was several $100 million to $1.5 billion, sure, where program development teams were several dozen people to several hundred people. And my perception is that this CREW is very tail end centric. And as an integration and test guy, I certainly know that when you get to that point in the program, this is not the thing that program management wants to know anything about. Okay, so it's really how can this methodology be instantiated as a continuous quality process throughout the entire program, so that we don't have a large deviation, right? That if we do have a deviation, it's small, and the remaining risk is small, and we're going to get a fielding decision, right? Because once you spend $1 billion, it gets fielded.
Jeff, that's a great question, and let me give you some practical experience from what I've seen in the world that I live in. What we find is, and what I've seen on multiple occasions, when there is challenges during integration, if we have this common set of questions on the front side, with integration package 1, what does my quality look like? If I have problems integrating, if I have problems with multiple sets of vendors, if I have problems identifying what's being passed over certain communication buses, and I want to truly understand what's going on, I take a snapshot with iteration 1. 6 months later, I got another drop. What does that look like? Is that better or worse? If it's better, where's it better at? If it's worse, where's it worse at? Iteration 3, iteration 4, etc. And so now, after a course of, say, a large integration over a multi-year period, I have some trending numbers. I have trending numbers not only for one particular processor, but I might have them for multiple vendors that are integrating with me as well. And by providing them feedback as to the results, I am now indirectly guiding them to what I find is most important from a vendor standpoint. Hey, if you're not giving me diagnostic information, I kind of need that. I consider that to be a quality problem. If you're not following criticality standards like the secure coding rules that exist out there, that might be a problem. I want you to start following those. And so I'm providing that information back to a vendor and guiding their development process. Whether they have written that in contract or not, they're seeing what I'm looking at that's coming out of their shop.
Understand. Okay.
Could I comment on that as well? I think about this from a time perspective. I think it's the items that have been listed. What you want to do is really impose those up front. Let's say you start halfway through a project or quarter way through a project, and that's very common. You're right, and it's very rare that you start with a clean slate. But let's say about 20% of the project, you have to establish this is are going to be our style. This is how the unit tests are going to be written. And if you have like we do, I come from a very similar background. Both of you guys are talking about $100 billion projects for the defense industry typically, and people all over the world doing the development. But one of the things we try to do is, and I'm one of those proponents, I say, before you get this contract, guys, these are our standards. You need to have this critical standard function. Unit tests are going to be written this way. This is going to be MISRA, for example, or whatever are you going to check at the end. And you're right that when this is delivered, whatever you're going to check, you tell them up front, this is what we are going to check. This is how you need to do it. So to answer your question, I think I would say it's not necessarily applied at the end. You do checking at the end, but you establish the rules up front. So that's been my successful experience with that. It's too late when and commonly when it is said, "Oh, this is not right. You should have done this way." They said, "Hey, we have spent already $50 million. We are not going to do this again. Sure, if you would give us another $50 million." So whatever you're going to check, establish up front. So that was my 2 cents.
Thank you, Bashir, and I would absolutely concur with everything you just said there. Unfortunately, for at least some of the projects that I've worked on, that hasn't always been the case, and it always hasn't been the case that it's established up front, knowing that a lot of the procurement folks don't have that level of a software background, and that they're focused primarily on requirements and meeting requirements. So if challenges evolve in the development lifecycle, systems engineers are often found to go fix large challenges. And if they're not, to your point, in an ideal world, that would have been established up the front side. But if they're not, then we have to have some mechanism, some tool in the tool bag to modify and direct those particular changes and understand where they lie at, even late in the program and life cycle of the development side.
And the acquirer has to request it so that it gets costed and so that systems engineers can do the work.
I would agree with you, Jeff. 100%. I agree with you.
Michael, I just wanted to that's not necessary. Michael, I wanted to share a comment from Philip.
Sure.
Bashir said it well. If you know these things up front, how your code quality is going to be measured up front, and you know what a program is checking for, then you can do these checks yourself and produce the results. So,
very true.
Yes.
Very true. Yeah, I completely. I mean, when you're looking at a project from the front side, and there's a lot of clean territory, all of those comments are absolutely completely applicable. In the world that I have unfortunately lived in, not everything is that clean on the front side, and we have to solve these problems somehow, and we have to take what we have available to us. Even late in the game, and even late in the process, even in many cases after initial delivery, and we have to fix things, especially during the integration period across multiple vendors. So this type of a process is for that. It's for solving the challenges late in the game when we have integration or we have system problems that have to come together in order to make an overall package or product work. Yeah, but I would agree with everything Jeff and Bashir said. I really would.
Yeah, I think, Mike, it's a, getting in the contract, like Jeff said as well, getting in early. We've done that with like ATAMs where, ATAMs, sometimes it's like shooting fish in a barrel. We do these evaluations and they really didn't understand the criteria and what the customer wanted. And there are lots of risks because the architects, not that they did a bad job, it's they didn't really understand or know the requirements. And so if you know these, and when we get this, in the contracts earlier, those evaluations go well. And I think if you could get these checks in there early, you could use the CREW method as part of an overall mitigation strategy early in the life cycle too. I think there's a lot of value there.
I would agree. I would 100% agree with you, Phil.
Awesome. Thank you, Philip. Thank you, Jeff and Bashir. Parsa had an interesting question following up on Philip's comment, where can we find more information on the CREW worksheet? Is this worksheet and the process available online and for review?
Great question. Great question.
Yeah.
So at the end here, I'll be passing the slides that we talked through today. But it's important to recognize that we work in the embedded space and we have specific sets of needs for our customers. Not everyone, not as a systems engineer, not everyone lives in that space. As we talked earlier, things along the lines of user interfaces. Well, questions really need to be developed. And the key aspects and the key focus areas for a project that has user interface need. Now that would need to be, we need to develop questions, or an organization would need to develop questions there. The same is true for data-centric type projects. The same is true for languages that are not necessarily C and C++. So like I said, we'll give you the slides on the backside of this. But the real need here is for organizations to recognize that they have to carve out their own set of foundational questions of where they believe the quality of their source code is best measured. Over.
Awesome. So with that, is there any other questions that people want to ask? Please feel free to either raise your hand or post in the chat. Okay. Well, let's conclude our talk. This talk, again, will be posted on our YouTube channel, and we will send a follow-up email to everyone that registered. I did get some stats. We have over 10 countries registered and over 400 for the series. So that's amazing, and it just keeps growing. Our next session, again, we'll send everyone the link for that as well. But again, you have to register to through that link to get the link for the Zoom call. With that, Michael, thank you very much. Thank you, everyone, for participating. Thank you, Jack, for being an amazing tech host and organizer of these series. If you want to unmute or show your screen, everyone. If anyone would like, I've been taking the screenshots and posting them on LinkedIn for everyone who's participating. So if you want to turn on your camera, and I'll just take a quick screenshot for anyone that might want to. I think as engineers, most of us are kind of like, yeah, I'll just keep my name up, but I'll do that right now. So awesome. Thank you, everyone. Have a great afternoon. Thank you for spending your lunch with us, or in other parts of the world, wherever, dinner, breakfast. Awesome.
Awesome.
Bye, everyone.
Thank you.
Thank you. you.